On the morning of June 30th, 1908, the remote Siberian wilderness was waking to a calm summer day. At approximately 7:17 in the morning local time, a strange, brilliant light streaked across the sky, described by witnesses as a bluish ball with a fiery tail or a diffuse glowing star. Indigenous Evenki people and Russian settlers watched in astonishment as the light moved at incredible speed across the horizon, culminating near the Podkamennaya Tunguska River. Moments later, the sky erupted in an enormous blast, generating a pillar of fire and a cloud of dark smoke. The shockwave from the explosion was so powerful that it knocked people off their feet over 60 kilometers away, shattered windows, and registered on barometers as far as England. One man, S. Semenoff, sitting on the porch of a trading post 65 kilometers from the explosion, reported being thrown several feet and feeling an intense heat that seemed to set his clothing alight. Despite the enormous energy released, estimated to be up to 1,000 times that of the Hiroshima atomic bomb, the event went largely unnoticed by the outside world due to the region's isolation and sparse population. Over the following nights, a strange atmospheric phenomenon occurred, a lingering glow in the sky across Asia and Europe, allowing people to read newspapers outdoors at midnight, signaling that millions of tons of dust and ice had been thrown into the upper atmosphere by the blast. Although the Tunguska explosion occurred in 1908, the wider scientific world did not fully investigate the event until over a decade later. In 1921, Russian mineralogist Leonid Kulik began collecting eyewitness accounts and reports, determined to uncover the truth behind what locals described as a falling star and a devastating explosion. His initial survey faced incredible challenges. The suspected impact zone was hundreds of kilometers from the nearest railway, and the Siberian wilderness was filled with dense forests, swamps, and rivers. Kulik's first attempt to reach the area failed, but he returned persistently, aided by local Evenki guides who knew the terrain intimately. By 1927, nearly 2 decades after the explosion, Kulik and his team finally reached the site. What they discovered was shocking. The forest over an area of more than 2,000 square kilometers had been flattened, yet not in a uniform manner. Trees were knocked down in a radial pattern, pointing away from a central point, creating a butterfly-shaped devastation visible even from aerial photographs years later. In the very center of the blast, however, the trees were not uprooted. They stood like scorched telegraph poles, stripped of branches and bark but otherwise intact. There was no crater, no fragments of a meteorite, and no conventional evidence of impact. The destruction was complete, yet paradoxically, the source of the energy remained invisible. Kulik meticulously documented these observations, measuring tree fall patterns and marking the radial extent of the devastation. He drained small bogs and examined depressions, suspecting impact craters, but found nothing. The more he investigated, the clearer it became that this explosion had been unlike anything seen before, an immense release of energy in midair, leaving a giant swath of destroyed forest, but no tangible object behind. This journey highlighted both the scale of the catastrophe and the enduring mystery of what had caused it. The remoteness of the Tunguska site, combined with the sheer magnitude of the destruction, delayed scientific understanding for decades. Even after Kulik's expeditions, the world had only glimpsed the enormity of the event through reports and photographs. His findings laid the foundation for decades of investigation, giving scientists the first clear evidence of an unparalleled atmospheric explosion that challenged traditional ideas of meteoric impacts and left the Siberian wilderness a silent testament to nature's raw power. After Kulik's groundbreaking expeditions in 1927, scientists began to piece together what might have caused the Tunguska event, but the puzzle was far from complete. The most widely accepted explanation that eventually emerged is known as the airburst hypothesis. According to this theory, the Tunguska object, either a stony asteroid or an icy comet, never actually impacted the ground. Instead, it entered Earth's atmosphere at an extremely high speed, estimated to exceed 50,000 kilometers per hour. The immense friction and pressure caused the object to heat up, disintegrate, and explode in midair, roughly 5 to 10 kilometers above the forest canopy. This midair explosion explains several of the baffling observations from the site. The trees at ground zero were stripped of branches and bark, but left standing, while the surrounding forest was flattened in a radial, butterfly-shaped pattern. The airburst released energy equivalent to approximately 10 to 30 megatons of TNT, hundreds of times more powerful than the bomb dropped on Hiroshima. Shock waves from the explosion were recorded by barometers as far away as England, demonstrating the extraordinary reach of the blast. Unlike typical meteorite impacts, no large fragments of the Tunguska object survived to reach the ground, which is why Kulik and later scientists could not locate a crater or recover meteorite pieces. Evidence supporting the airburst theory continued to accumulate over the decades. Analysis of tree resin and peat bog layers from the area revealed microscopic silicate and magnetite spherules, enriched with nickel, a hallmark of extraterrestrial material. Elevated levels of iridium, a rare element often associated with asteroids, were also detected in soil layers dating from 1908. Together, these findings reinforced the conclusion that a cosmic object had exploded in the atmosphere rather than striking the Earth directly. The airburst theory also gained a modern parallel with the Chelyabinsk meteor in Russia on February 15, 2013. A roughly 20-meter asteroid exploded in the atmosphere, shattering windows and injuring over 1,500 people. Though much smaller than Tunguska, the Chelyabinsk event provided a tangible example of how an object could release massive energy in midair without creating a crater. By comparing Chelyabinsk to Tunguska, scientists were able to refine their models, estimating the energy, altitude, and trajectory of the Tunguska explosion with greater accuracy. Despite this consensus, questions remained about the object's composition. Was it a dense, stony asteroid, a fragile comet, or a rare type of iron-rich meteoroid? Computer simulations suggested that a stony body between 50 and 80 meters in diameter best matched the observed damage patterns and energy release. Some researchers proposed that a large iron asteroid might have grazed the atmosphere and partially skipped back into space, but this scenario remains speculative. Regardless of the exact type, the evidence increasingly pointed to a cosmic origin and a high-altitude detonation as the explanation for the unprecedented destruction. By the mid-20th century, the Tunguska event had become a benchmark for understanding atmospheric explosions of cosmic objects. Scientists recognized that such airbursts could cause massive regional damage without leaving conventional impact evidence. The mystery of the missing crater, once baffling Kulik, was now explained by a combination of velocity, altitude, and the object's explosive disintegration in the sky. Yet even with this mainstream explanation, the event retained an aura of the strange and inexplicable, a reminder that nature could unleash incomprehensible power far above the ground, leaving almost no trace of the weapon that had done it. The Tunguska event also prompted renewed interest in planetary defense. By studying past airbursts and near-Earth objects, scientists began to understand the potential threat such events pose to populated areas. Today, Tunguska serves as both a historical oddity and a cautionary tale. A cosmic event capable of leveling vast tracts of forest, demonstrating the fine line between natural wonder and catastrophic destruction. Even with the airburst hypothesis providing a solid scientific explanation, the Tunguska event continued to fascinate and confound both scientists and the public, inspiring numerous fringe theories. The lack of a crater and the near total disappearance of the object left room for speculation that ranged from the imaginative to the outright fantastical. One of the most enduring ideas was that the explosion had been caused by a crashing extraterrestrial spacecraft. Sci-fi author Alexander Kazantsev, writing after the atomic bombings of Hiroshima and Nagasaki, suggested that a UFO powered by a nuclear engine might have detonated over Siberia. He pointed to the radial destruction pattern and the intense energy release as evidence, comparing it to a small-scale nuclear explosion. While visually compelling, there is no empirical evidence to support this claim, and it remains purely speculative. Another proposed explanation involved exotic physics. In 1973, some physicists hypothesized that a miniature black hole could have passed through the Earth at Tunguska, creating a catastrophic shockwave without leaving any conventional impact evidence. In this scenario, the black hole would have entered the atmosphere, released an immense amount of energy, and exited on the opposite side of the planet. Although theoretically testable, predicting disturbances or energy signatures at the exit point, no such evidence was ever observed, making this idea extremely unlikely. A third, equally speculative theory involved antimatter. Scientists proposed that a small chunk of antimatter might have collided with the Earth, annihilating itself and releasing enormous energy while leaving no debris. In practice, large amounts of antimatter do not naturally exist in our solar system, making this explanation virtually impossible. yet it persisted in popular discussions, largely because it accounted for the total disappearance of the object. Even Nikola Tesla was pulled into the conversation. Some conspiracy theorists claimed that Tesla had been testing a long-range wireless energy weapon, a death ray, and that the Tunguska blast was an accidental discharge directed at the unpopulated Siberian wilderness. Proponents imagined that Tesla had attempted to bounce massive electrical energy off the ionosphere and inadvertently triggered the explosion. While this theory is dramatic, there is no credible historical evidence linking Tesla to the Tunguska event, and it remains a modern myth. Other ideas included natural but unusual phenomena, such as a massive volcanic gas explosion from a previously unknown Siberian vent, or a sudden release of methane from permafrost. Both were largely discounted because no supporting geological evidence was found, and the radial tree fall pattern matched a high-energy aerial explosion rather than a ground-based release. Despite the lack of supporting evidence, these fringe theories served an important role in the public imagination. They highlighted how a single unexplained event could challenge conventional thinking and spark creative, if scientifically unsupported, explanations. The combination of immense power, the absence of physical remnants, and the sheer isolation of the event contributed to Tunguska's reputation as one of the weirdest events in recorded history. Ultimately, while these alternative explanations are intriguing, they cannot compete with the airburst hypothesis, supported by modern measurements, chemical analysis, and computer modeling. Nevertheless, the persistence of these ideas illustrates the deep human desire to understand mysteries that seem almost supernatural. Tunguska became more than just a historical explosion. It became a symbol of the unknown forces that lurk above our planet, waiting for a rare, devastating moment to remind humanity of its vulnerability. After more than a century of study, the scientific consensus has largely settled on the Tunguska event being caused by the airburst of a cosmic body, likely a stony asteroid or comet, that exploded in the atmosphere without ever touching the ground. Detailed computer modeling suggests the object was between 50 and 80 meters in diameter and detonated with the energy of 10 to 30 megatons of TNT. This mid-air explosion explains the unique butterfly pattern of flattened trees, the standing but scorched trees at the epicenter, and the absence of a crater. Subsequent expeditions to the site uncovered tiny silicate and magnetite spherules embedded in soil and tree resin. These microscopic spheres contained elevated levels of nickel, a classic indicator of extraterrestrial origin. Analysis of peat bogs in the region also revealed a distinct layer dating to 1908 with higher than normal concentrations of iridium, an element rare on Earth but common in meteorites. These findings strongly support the hypothesis that a cosmic object entered Earth's atmosphere and exploded, leaving only trace evidence of its presence. The Chelyabinsk meteor in Russia, which exploded in February 2013, provided a modern analog. At about 20 meters in size, it created a powerful airburst that shattered windows and injured over 1,500 people, demonstrating on a smaller scale how a fast-moving object can release enormous energy in the sky. Scientists now understand that such airbursts can flatten forests, create shockwaves over hundreds of kilometers, and produce bright, lingering atmospheric effects without leaving a crater. Debate continues over whether the Tunguska object was a comet composed mostly of ice or a denser, rocky asteroid. Some models suggest that a cometary body would account for the bright, glowing skies observed across Europe and Asia for several nights after the explosion. However, most recent analyses favor a stony asteroid, based on calculations of density, entry angle, and energy release, which better explain the pattern of destruction observed in the Tunguska forest. Beyond solving the mystery of Tunguska itself, this event has become a crucial case study for planetary defense. Scientists use the data to model potential near-Earth object impacts, simulate atmospheric explosions, and develop early warning systems. Tunguska illustrates that even relatively small cosmic objects can unleash destruction comparable to the largest nuclear weapons. The event also serves as a cautionary reminder of how rare but high-impact cosmic phenomena can threaten human civilization. It underscores the need for continued investment in asteroid detection, monitoring, and, if necessary, deflection technologies. International efforts, including NASA's DART mission and other planetary defense initiatives, aim to prevent future disasters on a global scale. While the mystery of Tunguska has largely been resolved scientifically, Its legacy continues to inspire awe, caution, and curiosity. It reminds humanity that Earth is not isolated from the cosmos, and that even the most remote and sparsely populated regions are vulnerable to forces far beyond human control. Tunguska remains a singular example of a natural event that is as educational as it is terrifying. The Tunguska Event of June 30th, 1908 remains one of the most bizarre and unsettling occurrences in modern history. While scientists have largely confirmed that a mid-air explosion of a cosmic object caused the devastation, the sheer scale and unusual characteristics of the event continue to capture imaginations. From the flattened forests over 2,000 square kilometers to the standing but scorched trees at ground zero, every detail underscores the extraordinary force released by the explosion. The event also serves as a stark reminder of humanity's vulnerability to cosmic hazards. Objects in space, even relatively small ones, can release energy equivalent to dozens of nuclear bombs without warning. Had the Tunguska object exploded over a populated city instead of the remote Siberian wilderness, the consequences could have been catastrophic, potentially killing tens of thousands and causing unimaginable destruction. This scenario illustrates why planetary defense is not just theoretical. It is a real, urgent priority for scientists worldwide. Since Tunguska, international space agencies have invested heavily in detecting and tracking near-Earth objects. Programs like NASA's DART mission, which successfully altered an asteroid's trajectory, show that technological solutions exist to mitigate potential threats. Additionally, global awareness campaigns such as International Asteroid Day on June 30th educate the public about the dangers of space hazards and the importance of scientific monitoring. The Tunguska explosion also continues to fuel curiosity and debate. Fringe theories, from alien spacecraft to miniature black holes, may have no scientific basis, but they highlight how a mysterious event can inspire both wonder and speculation. In reality, the true story is compelling enough: a cosmic visitor traveling millions of kilometers through space, disintegrating in our atmosphere, and leaving behind a scar on the Siberian forest that remains visible more than a century later. Even today, researchers revisit the Tunguska site, studying tree rings, soil layers, and atmospheric data to refine models of airburst phenomena. These investigations help predict how similar events might unfold and improve our understanding of the physics behind cosmic explosions. Every new piece of data reinforces the lesson that Earth exists in a dynamic and sometimes dangerous cosmic environment. Ultimately, the Tunguska event is a reminder of both the fragility and resilience of life on Earth. While it exposed how vulnerable human settlements can be to rare cosmic phenomena, it also prompted scientific innovation and preparedness that could save countless lives in the future. By studying the past, humanity learns to anticipate and survive potential threats from beyond our planet. The legacy of Tunguska is therefore twofold: a chilling historical record of one of nature's most powerful airbursts, and a continuing call to vigilance, research, and planetary defense. It is a story of mystery, destruction, and scientific triumph, an event that transformed a quiet Siberian wilderness into a cautionary tale for the entire world. The memory of that bright, terrifying morning on June 30th, 1908, remains etched into both the Earth and human consciousness, serving as a final warning from the cosmos itself. Before August 20th, 1986, the villages surrounding Lake Nyos in Cameroon were quiet, peaceful places. Communities like Nyos, Kam, and Subum thrived in fertile valleys, where the rich volcanic soil made farming and raising cattle abundant and reliable. The lake itself, sitting in the crater of an ancient volcano, was calm and clear, a serene presence that shaped daily life without causing concern. Children played in open fields, while families tended to livestock and household tasks, and the evenings were often calm and ordinary. Locals had lived beside the lake for generations, unaware that beneath its placid surface lay a hidden threat. The night before the disaster, the village was unusually quiet, a stillness that, in hindsight, was almost ominous. No one could have predicted that the air they would breathe hours later would become deadly, or that the lake they relied on would erupt with an invisible killer. This ordinary evening set the stage for one of the strangest and deadliest natural disasters in modern history, hidden beneath the surface of a peaceful highland lake. As night fell on August the 21st, 1986, a deep rumbling sound echoed faintly across the hills near Lake Nyos. Some villagers described it as a distant explosion, unusual and unsettling, but they did not suspect the catastrophe that would follow. Soon, a dense white cloud began rising from the lake, unlike any fog or mist they had seen before. This massive plume of gas, more than 300 feet thick, flowed silently over the crater's edge, heavier than air, and descended into the valleys below. It moved like a creeping river of suffocation, hugging the ground as it advanced, leaving no time for escape. Survivors on higher ground watched helplessly as the cloud swallowed homes, fields, and livestock, while others smelled a strange odor reminiscent of gunpowder or rotten eggs just before losing consciousness. The gas was almost pure carbon dioxide, displacing oxygen and causing instant asphyxiation at the concentrations present that night. Within minutes, the villages were eerily silent, with people and animals alike collapsing where they stood, and the invisible killer had claimed its first victims. When the sun rose on August 22nd, 1986, the world around Lake Nyos was unrecognizable. Villages that had been lively just hours before were now completely lifeless. Those few who had survived by climbing to higher ground or staying near the crater's edge returned to a scene of unimaginable horror. In Nyos, only 4 people remained alive out of hundreds. In nearby villages such as Kam and Subum, entire communities had vanished. The bodies of men, women, and children lay in homes, in fields, and along pathways, with no visible wounds or signs of struggle. Livestock had also perished. An estimated 3,500 cattle and countless goats, sheep, and other animals lay dead across the fertile valleys. Birds and insects had been suffocated as well, leaving an eerie quiet that extended at least 14 miles from the lake's edge. The lake itself bore witness to the disaster. Normally clear, the water had turned a deep reddish brown, a result of iron-rich water from the lake's depths, reacting with the oxygen it suddenly encountered. Its surface had dropped by about 3 feet, and trees along the shoreline were flattened as if struck by a powerful force. Investigators later discovered that many survivors had been unconscious for as long as 36 hours, waking to find their entire families and neighbors gone. Joseph Naquain, a resident of Subum, described stepping outside to see no familiar faces, only silence and devastation. Emergency response was slow due to the remoteness of the area and the shock experienced by nearby towns. Villagers from further away and some government officials arrived to find the scale of the disaster nearly impossible to comprehend. They carried the few survivors to temporary shelters and hospitals, where around 300 people were treated for respiratory distress, nausea, and strange pressure-related skin lesions. These wounds were initially mistaken for chemical burns, but were later understood to be the result of long periods of unconsciousness combined with environmental exposure. The human toll was staggering, but the environmental impact was equally catastrophic. Trees along the slopes of the crater were stripped of leaves or snapped entirely. Crops in the valleys below were buried under a layer of gas-induced frost and chemical residues from the sudden carbon dioxide release. The quiet devastation left a haunting lesson. A lake that had appeared tranquil and life-giving had silently transformed into an agent of mass destruction. The scale of the disaster stunned both the local population and the scientific community, raising urgent questions about how a body of water could contain such a lethal force, and what measures could prevent it from happening again. In the days following August 22, 1986, scientists and government officials arrived at Lake Nyos to investigate what had caused such an unprecedented disaster. Initial speculation ranged from chemical leaks to volcanic eruptions, as survivors had reported a strange smell, often described as rotten eggs, in the moments before losing consciousness. But careful examination revealed no signs of explosive activity, no lava, no ash, and no chemical residue, capable of causing immediate mass fatalities. Instead, water samples taken from the lake's depths revealed an astonishing concentration of dissolved carbon dioxide. The gas had been trapped for decades, perhaps centuries, under the immense pressure of the 600-foot deep lake. Researchers quickly identified the disaster as a limnic eruption, a phenomenon virtually unknown at the time. Lake Nyos, lying in a volcanic crater, had accumulated carbon dioxide released slowly from magma beneath the Earth's surface. Because the gas was heavier than air, it had formed a layer in the deep water without mixing with the upper layers. On the night of August 21st, some disturbance, possibly a minor landslide, a tremor, or even heavy rainfall, caused the deep gas-saturated water to rise. As it neared the surface, the pressure dropped and the dissolved carbon dioxide rapidly escaped, forming a massive cloud that flowed over the crater rim. This eruption expelled roughly 1.2 cubic kilometers of carbon dioxide in a matter of minutes. Scientists soon realized the deadly gas behaved like a liquid that hugged the ground, displacing oxygen and suffocating everything in its path. The reddish-brown coloration of the lake was explained by iron hydroxide, formed as iron-rich water met oxygen during the eruption. The mechanism, while now understood, was terrifying. A serene lake had been transformed into a silent killer, releasing an invisible, odorless gas capable of erasing entire communities in moments. The Lake Nyos event also prompted a review of other crater lakes worldwide. Just 2 years earlier, Lake Manoon, also in Cameroon, had claimed 37 lives through a similar, though smaller, limnic eruption. Scientists recognized that without intervention, Nyos could erupt again, potentially within 15 to 30 years. This realization sparked urgent international efforts to design engineering solutions capable of preventing future tragedies. The discovery of the limnic eruption mechanism represented both a scientific breakthrough and a chilling reminder of nature's hidden dangers. In the aftermath of the Lake Nyos disaster, attention shifted from understanding the eruption to preventing another catastrophe. Approximately 4,000 people were evacuated from villages around the lake, with survivors relocated to resettlement areas like Kimbi and Bwabwa. Life in these camps was challenging. Housing was often inadequate, sanitation limited, and access to schools and healthcare sparse. Some children had to walk 7 kilometers to attend school, highlighting the long-term struggles faced by displaced communities. Psychological trauma ran deep as survivors coped with the sudden loss of entire families and neighbors. The Cameroonian government pledged to support reconstruction, but for decades, much of this aid was delayed or incomplete. To address the ongoing threat, scientists and engineers devised an innovative solution: degassing pipes. The first pipe was installed in 2001, with 2 additional pipes added in 2011. These pipes extract carbon dioxide from the deep layers of the lake in a controlled manner, allowing the gas to escape safely into the atmosphere. The process is self-sustaining, as water rising through the pipe reduces pressure and continuously releases gas. By 2019, the system had successfully lowered carbon dioxide concentrations to safe levels, effectively preventing another limnic eruption. The disaster at Lake Nyos also influenced global awareness of other volcanic lakes, such as Lake Kivu, which borders the Democratic Republic of Congo and Rwanda. Lake Kivu contains both carbon dioxide and methane gas, posing a potential threat to over 2 million residents along its shores. The monitoring and degassing technology developed for Nyos now serves as a blueprint for mitigating these risks. Ultimately, Lake Nyos remains a stark reminder of nature's hidden dangers and the importance of science in disaster prevention. While the tragedy claimed 1,746 lives, it also spurred international collaboration, engineering, innovation, and scientific understanding that continue to save lives. The survivors and communities displaced by the eruption still live with its legacy, but today the lake is monitored, controlled, and far safer than it was on that silent night of August 21st, 1986. The Lake Nyos disaster teaches us that some of the most deadly forces in nature are invisible, and only knowledge, vigilance, and preparation can protect humanity from repeating history. In early January 1953, Northern Europe was quietly enduring winter. Along the coast of the Netherlands, Belgium, and eastern England, communities were still rebuilding from the scars of the Second World War. Many towns relied on centuries-old dikes and levees to protect them from the North Sea, but years of neglect and limited resources had left these defenses weak. The relationship between humans and the sea had always been delicate, a balance built over generations, and on this night that balance would shatter. Far to the northwest, near Iceland, a deep low-pressure system began forming on January 29th. Meteorologists of the time recognized it as a fast-developing storm, but weather forecasting in the early 1950s was rudimentary, and most coastal residents had no idea what was approaching. This weather bomb intensified rapidly, producing hurricane-force winds that pushed massive amounts of water toward the southern North Sea. The timing could not have been worse. The storm coincided with a high spring tide when the gravitational pull of the sun and moon combined to create unusually high sea levels. The geography of the North Sea acted like a natural amplifier. Its funnel shape, narrowing between Britain and the Netherlands, forced the surging waters into a smaller area, increasing the height of the tide. By the night of January 31st, the sea level in some locations rose to more than 5.6 meters above normal, or nearly 18 feet. The winds continued to lash the surface, creating waves that crashed against fragile dikes already weakened by age and wartime neglect. Communication failures made matters worse. Radio broadcasts were limited, especially overnight, and few warnings reached the people sleeping in coastal villages. In Zeeland, Essex, and Lincolnshire, the residents were unaware that a monstrous surge was racing toward them. Every mile of coastline became a potential disaster zone, and when the water finally struck, it would come with virtually no warning. By the evening of January 31st, the stage was set. Tens of thousands of people would face one of the deadliest natural disasters of the 20th century. The North Sea, long both a source of sustenance and danger, was about to unleash its full fury on Europe, and no one could escape its reach. As darkness fell on January 31st, 1953, the storm surge finally reached the coast of eastern England and the Netherlands. In Lincolnshire, Norfolk, and Essex, the sea did not rise slowly. It surged violently, breaching dikes that had been trusted for centuries. Over 1,200 breaks appeared in Britain's sea defenses, and icy water poured into villages before most residents even realized the danger. In some towns, water levels rose so quickly that people had only minutes to escape or find shelter. On Canvey Island, the rising waves overwhelmed the seawall. Thousands of prefabricated homes built after the war and offering almost no resistance were instantly flooded. Residents scrambled to attics and rooftops, clinging to furniture or each other as the freezing water poured in. In one small village, an 80-year-old woman survived 3 days trapped on her dining table, clinging desperately to life as the tide refused to recede. Entire streets were transformed into rivers of icy water, carrying debris and livestock along with the people who had tried to stay behind. Across the North Sea, the Netherlands faced an even larger catastrophe. Much of Zeeland and the surrounding provinces lie below sea level, protected only by a complex network of dikes and canals. Between 4 and 6 in the morning, as the first light of day approached, the dikes began to fail. Water rushed in with terrifying force, sweeping away houses and farmland in minutes. Entire villages vanished under the relentless surge, while residents fled to higher ground or climbed into attics, praying that someone would come to rescue them. Tragically, the destruction was swift and deadly. People were caught off guard, many trapped in homes or knocked into the frigid floodwaters. Stories of survival were harrowing. Families holding on to one another for hours in freezing water, neighbors carrying each other to safety, and the haunting memory of those who could not escape. By the time the tide began to recede, thousands of homes had been destroyed, and the full scale of human suffering was only beginning to become apparent. By February 1st, 1953, the sun rose on a landscape unrecognizable to those who had fallen asleep just hours before. Towns were submerged under cold, murky waters, and roads and bridges had been destroyed, cutting off communication and complicating rescue efforts. In the Netherlands, approximately 9% of all farmland was underwater, leaving crops ruined and livestock stranded. Across eastern England, around 160,000 acres of land were swamped, including homes, schools, and churches, leaving thousands homeless in the dead of winter. The human cost was staggering. In the Netherlands, 1,836 people lost their lives, while in the United Kingdom, 307 died on land, with additional casualties at sea. Belgium, Scotland, and other coastal areas also suffered losses, bringing the combined death toll to nearly 2,500. Entire communities were displaced, and survivors faced freezing temperatures, contaminated water, and the constant threat of disease. Relief agencies struggled to provide food, blankets, and clean drinking water, often using boats to navigate streets that had become canals. Rescue operations were immediate but perilous. In the UK, 30,000 military personnel and volunteers were deployed to help save those trapped in homes or stranded on rooftops. In the Netherlands, local fishermen became first responders, navigating flooded streets in small boats to pull neighbors to safety. Makeshift shelters were set up in schools, churches, and town halls, offering the only refuge from the ongoing cold and wet conditions. The psychological impact was profound. Families had lost everything: homes, possessions, and loved ones. Survivors described waking up to floating furniture, trapped animals, and water gushing through kitchens and living rooms. For children, the terror of clinging to a parent in freezing water was a memory that would last a lifetime. Communities mourned collectively while also beginning the monumental task of cleaning, repairing, and rebuilding In the face of what seemed like an insurmountable disaster, the devastation of the 1953 North Sea flood forced governments and engineers to rethink the way coastal protection was approached. In the Netherlands, the disaster led directly to the creation of the Delta Commission, a specialized task force charged with designing a system capable of preventing such widespread flooding in the future. Over the next 4 decades, this initiative resulted in the Delta Works, an extensive network of dams, sluices, locks, dikes, and storm surge barriers. The Oosterscheldekering, the largest of these structures, spans nearly 2 miles and features massive gates that can be closed to block incoming storm surges, a marvel of modern engineering and a cornerstone of Dutch flood defense. In the United Kingdom, authorities also moved to strengthen coastal resilience. The flood prompted the establishment of the Storm Tide Warning Service, a system designed to provide early alerts to communities at risk of coastal flooding. The event was also the primary catalyst for the Thames Barrier, a massive movable gate system completed in 1974 to protect central London from high tides and storm surges. These projects demonstrated that even after catastrophic loss, human ingenuity could create solutions capable of mitigating future disasters. Beyond construction, the flood influenced planning, policy, and awareness. Towns and cities revised building codes to ensure homes could better withstand sudden flooding. Emergency management procedures were overhauled, emphasizing evacuation plans, emergency shelters, and coordination between military, civil authorities, and local volunteers. In both the Netherlands and the UK, education programs were introduced to teach citizens how to respond in the event of another large-scale flood. The legacy of the 1953 flood extends even today. The structures and systems built in response have successfully prevented major casualties in subsequent storms and serve as a global model for flood management. Engineers and planners worldwide study these projects, applying lessons learned to vulnerable coastlines in Asia, North America, and other regions at risk of storm surges. While the flood itself was a tragedy, it catalyzed a transformation in how humans coexist with the sea, turning disaster into enduring innovation and resilience. The 1953 North Sea flood was not only a story of destruction, but also a testament to human courage and resilience. In the immediate aftermath, communities across the Netherlands, the United Kingdom, and Belgium faced impossible challenges. Families clung to rooftops for hours, entire towns were cut off by water, and livestock floated helplessly through flooded pastures. Despite the chaos, ordinary people became heroes. Fishermen navigated icy waters to rescue stranded neighbors. Neighbors supported each other through freezing nights, and volunteers from distant towns brought supplies to those isolated by the rising tide. Recovery took months and in some cases years. Entire villages had to be rebuilt from scratch. Farmland had to be drained and fertilized, and infrastructure restored. Governments quickly learned that rebuilding was not enough. Stronger defenses and better planning were essential. The lessons from 1953 led to permanent changes in flood management, early warning systems, and public preparedness programs, ensuring that future generations would be far better protected. The human cost was sobering. Nearly 2,500 people lost their lives, but the experience forged a stronger, more united response to natural disasters. Communities that survived the flood retained vivid memories of the event, passing down stories of survival and heroism to ensure history would not be forgotten. Memorials were built, and annual commemorations honor both the victims and the bravery of rescuers. Today, the North Sea coastlines are safer, thanks to massive engineering projects like the Delta Works in the Netherlands and the Thames Barrier in England. Yet the flood remains a stark reminder of nature's power and unpredictability, showing that even in highly developed regions, human life can be profoundly vulnerable to the forces of the sea. The 1953 North Sea flood continues to inspire scientists, engineers, and emergency planners to innovate and prepare, turning a devastating catastrophe into enduring lessons of resilience, foresight, and human ingenuity.